I put the formula down on the side, which is actually so I'm not going to prove the formula. I'm just going to maybe do a rough sketch of how the formula might have come about. And it's an integral, so it's probably one of those things where we would, like in Calc 2, everything we did in Calc 2 was you have these little pieces, you have some delta x, you add them all up, and then the summation becomes an integral, the Riemann sum business. So I'm just going to do kind of a rough sketch of that idea and see how they came up with this thing. So what I'll do is I'll start off with a curve similar to maybe what you guys were looking at. And you have t some starting point and t is equal to b some ending point. So from a to b, t values a to b, you got x and or a and x and y values. And so we would partition our t-axis if we had a t-axis. We would partition that, say t0 is a, t1, t2, t3, all the way up to t sub n, depending on what the partitions were. And then for each of those partitions, we get, for each of those t values in the partitions, we get a point associated with it. So we get all these points. And so let's say we're looking at t sub I minus 1 and t sub I. As the t values you would put in your parametric equations. I didn't set this up properly because I'm trying to go fast, but for parametric equations, x equals x of t, y equals y of t. I guess it's already up here, but in your parametric equations, you would put in t sub I minus 1 and t sub I, and then you would get these 2 points somewhere in the middle. And then you would find the length or the distance between those 2 points. So what is the distance between those 2 points? Oh, how do you find a distance? So if we put that into t, or into the x value and the y value, you get this. This is an actual point. So the actual point has an x of t sub I minus 1, comma, y sub t, y of t sub I minus 1. And then this point over here would be x of t sub I, y of t sub I. And we're interested in finding the distance. Now, do you guys remember how to find the distance between 2 points? The distance formula, right? Some difference with the x's, difference with the y's. You square them, you add them, you form a triangle or whatever. Anyways, x sub t sub I minus x sub t sub I minus 1 squared plus y t sub I minus y t sub I minus 1 squared. So that's what you have. And if you look close enough, close enough. Oh, let's look closer. Right? If you look close enough, you're really looking at the slope of that line. Right? You can think about it as a slope. So that's where the derivatives come in, and those distances or the differences between them can just be like the derivative. And so So somehow this is going to become, your distances will become v sub I is going to equal to x prime at I minus 1. I guess it doesn't matter which one, if it's I or I minus 1, y prime t sub I minus 1. And then there's a delta t measurement to tell you like how much you're moving along the t. And so you put that in an integral, and then it becomes the formula that we just saw. So we add up all the arc lengths. And that's actually what I was going to have you do, is just, except it was going to be too small. Instead of using the string, I was going to have you guys just take a little toothpick and cut it really small, and then make the measurements like to stack up those toothpicks along the x-axis or along the curve, so that your graph would kind of look like it's made of straight lines, but small straight lines, so eventually it looks like a curve. And then I was going to have you add those things up, but I went with a string instead. So you add up the arc lengths, and so this Riemann sum will eventually become, I guess they call it L. For some reason they call it S. Okay, so that's the formula for the arc length. Do you guys remember what you guys got in your graphs? Yeah, but the answer.
Oh yeah, so we guessed like 6.5.
Uh-huh.
And it was actually 6.5.
Good guess. We will be, the computational part of your exams will require you to solve integrals. Now, I can assume that you passed Calc 2 and then you know how to integrate, but let's just say, in case you don't know how to integrate, you should at least be able to put your integrals in some sort of program where you can get numerical answers. So I encourage you to figure out how to do integrals in Wolfram Alpha, Symbolab, whatever else, and your calculators. Your calculators can also do them. Because I'm going to be interested in this class, I'm going to be more interested in having you set up the integrals than to compute the integrals. Although computing the integrals is sometimes important because we want to get a result. But I'm not going to stress the computation of integrals as much as setting up the integrals. And so when it comes down to doing stuff like that, that's what I'm more interested in having you guys do. So just to show you, I was told that you can also do integrals in Desmos, which is kind of cool. So here's the first one, groups 1 and 5. You got a 7.644-ish. Groups 2 and 6 should have gotten about 6.5, which is almost the same, or maybe exactly the same as the next group, group 3, group 7, and group 4 and group 8. We're looking at about a 5.2-ish. Oh, I forgot to tell you, for this last group, it turns out that this curve, so I was doing this, right? I was actually looking at this. I said, okay, I'm going to integrate from 0 to pi, and then this is what I got, right? So if I integrated from 0 to pi, I get 10 point something. But then I looked, right? I'm actually applying the exercise that I had you guys do on myself and saying, okay, if I were to look at this visually, you know, this little length in the first quadrant would be just a little bit about, it's about square root of 2, so it's not more than 2. So it's 1 point something. And then this little loop over here, it's probably close to 2, but not exactly 2. So that's 3, 4, 5-ish. So this thing is about 5 something units. And then the integral that I got was 10. So something's wrong here, at least visually as I was looking at it. That didn't look right. And so it turns out, you guys know what's wrong? It goes backwards and goes over itself. So starting from 0, that's pi over 2. And then it goes back and writes over it again. And so that's when I realized, oh, I probably just need to go to pi over 2. So I apologize for those people with the purple graph, but we'll take a look at it. Okay. I forgot. I meant to change it. I changed it in my worksheet, but I had already printed it, so I forgot to tell you guys. But in any case, this is why looking at an answer for my integral and looking at the actual graph had to make sense together. And when I was looking at it, it did not make sense. And it took me like 15 minutes to figure it out. Oh, what if it just repeated itself? Yeah. 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 That's fine. It's fine. It's the effort that counts. At least for these exercises, for the test, it's the numbers that count. All right. So there's no points for effort for that. I mean, whatever. Okay. That's arc length. Um, we're good with that, right? We don't have to do an example. Look at the book. There's also surface area, which is a surface area in this particular scenario. And I don't know if you guys actually went through this in your Calc 2 class, because this is one that if I didn't have time in my Calc 2 class, I would skip it. This is the surface area of revolution. So this is when you revolve a curve around a particular axis. And again, without really going over the details too much, I just want to show you kind of a short and informal justification of this particular formula. And you notice that there's an arc length involved, or at least the stuff in parentheses looks just like the arc length formula. And then there's this 2 pi y on the side. So what is that about? So just to give you, again, a kind of visual justification of this. This is revolved around the x-axis. So let's say you have this curve that's being revolved around the x-axis, and then you end up with a surface. And so in Calc 2, you guys did volumes of revolution. So you took a look at the volumes. But we're looking at specifically a surface. And so what we're doing here essentially is we're taking, just like the cuts that we did with the arc length, we could take those same cuts, but each of these cuts would have a specific length and they would get revolved around this axis. And so what do you get there is not a disc, but an actual cylinder, just the outside of the cylinder, where you have, if we look at the cylinder sideways, turn your head to the right, and it looks like a cylinder with a height of whatever the height is, and then it would have a radius of whatever the radius is. So if we look back at the picture where it was getting rotated, it looks like the radius is just a y value, right? From 0 to some y value of that particular graph or curve. And then the thickness here is just the arc length. And the arc length also contains your delta t. So that your arc length part over here is that. And then this is your height. So this is your height. This is your radius. And then the area, the surface area of the side of the cylinder is 2 pi RH. So there's this 2 pi. So the surface area is 2 pi RH, and you got your 2 pi, you got your radius R, and you got your height H accounted for. And so that's basically what we're doing, right? So when you have a parametric equation, you have an x of t and a y of t. So when I say y, you're really putting in y of t, right? Not just the y value, because you're integrating with respect to t here. So you need to put something with respect to t. So if we do let's see if we could do a quick example. So let's do an example where let's set up the integral to find the arc length, and then let's set up the integral if this was revolved around the y-axis, the x-axis, the arc length. So I think what an important part of this is the derivatives. So x of t is equal to 2t minus 3t squared. Y, that's x prime of t. Y prime of t is equal to 1 plus 4t cubed. And so if we wanted the arc length, the arc length is just going to be the integral from t is equal to 0 to 1. And then we have the square root. And then I would have 2t minus 3t squared quantity squared plus 1 plus 4t cubed quantity squared dt. And as far as Calc 3, we're done. And then now you go into Calc 2 mode where you would integrate this. And if you don't want to do that, you would punch it in some program. Now the surface area of revolution. If this was revolved around the x-axis, it's essentially the same thing, except there's a 2 pi and then the y. And so the y is literally this thing over here. And so I would just take that and put it in front of my integral. So surface area is the integral again from 0 to 1, 2 pi. And then the y was t plus t to the fourth. And then the exact same 2t minus 3t squared quantity squared plus 1 plus 4t cubed quantity squared dt. Okay, so that's it. So right now we're just like plugging stuff into formulas and then using a computer to calculate. All right, any questions? Now, if you're rotating around the y-axis instead of the x-axis, then can you imagine how the formula is going to change? X instead of y. And then the arc length is still going to be the arc length, so it's still going to be okay. All right, so think about that, process it, make a note for yourself. What happens if you, I'll make a note in my notes, but I'm not going to do anything about it. Is the formula if surface area is rotated, rotated, rotated. Is it too many T's? Shoot. Okay, so think about that, and then I'll move on. Questions? Except for this question. That's for you to answer. Yeah.
Are we waiting for the process of solving the integral or just try
For the computational part of the exam, I just want the answer, and your answer is going to be correct. Well, if you found if your integral is correct, so that's just one more step to plug it into the computer. No, I don't care about the process. I don't care about what did you use integration by parts or partial fractions. No, I don't care about that. No, not for that part. So I'm interested in you building this integral. After you built the integral, you pay somebody to compute it for you. That's where we're at right now. All right, let's move on. We're on to the next section. Oh, there's a curvature thing too, but we'll do curvature later. Polar coordinates. So what we're going to do is we're going to transform ourselves away from what we would normally call Cartesian coordinates into what we would call polar coordinates. And polar coordinates allow us to view our geometry in a way that, well, we may have not seen before. But in a way where we could be dealing with circles. So we found out on the first day there's going to be a lot of circles things around this class, and so we're going to keep going around in circles. As we study more of this stuff, polar coordinates is how we do things in circles. All right. And so what we want to do is we want to look at the relationship. We can take a look at the relationship graphically. There's an interesting geometry behind this relationship between x, y. Your x and y in your Cartesian coordinates versus how we're going to measure this in polar coordinates. So the way we're going to measure this in polar coordinates is that we introduce two new variables, r and theta. And then r and theta come from r, a radial distance, a distance from the origin to whatever point you're at. And then theta would be the angle from the positive x-axis up to the ray that makes that line, the length of r. Okay, so if we want to find the relationship between x and y, we can use trig, right? Opposite over hypotenuse is going to be your opposite over hypotenuse. It's going to be your y, and then adjacent over hypotenuse is your x. And then if you finagle those around, you're going to get the relationship between your polar coordinates and your Cartesian coordinates. More importantly, though, when we're doing these coordinate systems and we change from Cartesian to polar, I want you to notice what's actually happening. When we first learned to graph back in, what, second grade? When did you learn how to graph? We plotted points, right? Yeah, or ordered pair, x and y, and stuff like that, and then you put it into you move your x, you move along the horizontal x, you move along the vertical y, and then that's where you're at. And so the graph paper is actually important to look at when we're looking at Cartesian coordinates and how to switch to polar coordinates, because now instead of using x and y, when we move into polar coordinates, you don't label the axis r and theta, because that's not what r and theta is. I mean, you can if you go into the polar coordinate space, but if we're staying in x and y in polar coordinates, what is r again? Radial distance. So what if I say my r is equal to 1? If my r is equal to 1, I'm looking at a length of 1, right? But I'm looking at that length of 1, and you guys are already saying circle. Why? Why? Why are you saying circle?
All these points.
All these points come from a radial distance of 1 with just different values of theta, right? When I say x equals to 1, I say my x value is equal to 1, and it doesn't matter what my y value is. As long as my x is 1, I'm all good, right? So when I say r is equal to 1, my radial distance is 1, and it doesn't matter what my angle is, as long as my radial distance is 1, then that's where I am. So r is equal to 1 is literally, in polar coordinates, it's literally a circle. Do you guys ever use literally too much? Like the dictionary is going to redefine literally to not literally anymore. Yeah, that's right. It's too late. That was your generation, wasn't it? Somebody's, not mine. I'm too old for that shit. R is equal to 2, R is equal to 3, etc., etc. So I'll have radial distances away from the origin that would make circles. Now let's think about an angle. What if I say my angle is pi over 4? That's just a line, right? A line. And what if my angle is pi over 3, pi over 6? What if my angle is whatever my angle was? Okay, so when you buy graph paper and you buy graph paper, say my graph paper is in Cartesian coordinates, your graph paper looks like these things with squares. If you buy graph paper for polar coordinates, this is your graph paper for polar coordinates. You believe me? You can't always believe what I say. So, was it settings? This? Polar coordinate graph paper, right? Maybe, except they would probably go spherical coordinates. All right, so there's your polar coordinates. So, polar coordinates. That's r minus 1, r equals 1. So, if my r is some fixed value, it's just circles. I don't know if they would do this. Let's see. Theta equals pi over 4. No, you can't graph it. Sometimes they'd be able to graph theta is equal to pi over 4, which is those radial lines that go out. Okay? So, if you look at the relationship between the polar coordinates, usually you remember the right-hand side here where it says x equals r cosine theta, x equals r sin theta. But there's also the relationship between polar coordinates using r squared is equal to x squared plus y squared. So when r is equal to 1, here you have 1 is equal to x squared plus y squared, which is a circle of radius 1. At least that's how we know it as. And so that's really the graph that results in that. So when r is equal to 2, x squared plus y squared is equal to 2 squared. That's your circle of radius 2, etc. Okay. Now these rays going out here also should be acknowledged, and this would be your theta is equal to, say, pi over 4 or something. So those are graphs of these things. More interesting graphs would be if we take a look at graphs of things that are not just r equals 1 or r equals constants. What if we let r equal to some other value? Let's start off with r is equal to theta. What do you think that's going to look like? Imagine, close your eyes, or don't. The idea behind this is I had a pointer that I used to use in pointer. The idea behind polar coordinates is that as you go around, you get a measurement of theta. And as you go around with the measurement of theta, then your graph is going to do whatever it's going to do. So that's not getting recorded anymore. Markers. So imagine this as your number line for R, and imagine your number line. This is 0. This is, let's say this is 1, this is 2, this is 3, this is 4, this is 5. Those are your R values. Okay? So when my angle goes like this, and I start with R is equal to 1, this is 1 radian. Is about right here. Can you trace the drawing? Do you know how it's going to look like?
Spiral.
It's going to look like a spiral, right? So by the time I get to here, right, it's going to keep drawing this. And if this is theta, it's just going to get bigger and bigger as we go around. Okay. So we didn't have time for that exercise. That's what I wanted you guys to do. So if we draw r is equal to theta, as theta gets larger and larger, your radial distance gets larger and larger. So if you keep going around in circles and your radial distance keeps going out, then you just have a spiral. Oops. Cool. This is the one I said I was going to shrink and I forgot. I'm going to shrink it right now. For some reason it takes a while to. All right. So this is another interesting graph. It's just a spiral. Imagine, x squared, that's a spiral that's going to go up faster, or e to the x, or log x would be a spiral that's going to grow slower. In fact, I think it's sometimes called the logarithmic spiral. Maybe I'm just making that up. Whoa. I don't know. Wait, what's log of 0? Negative infinity, right? So speaking of negative numbers, if you have negative numbers in here, let's say this is 0, right? A negative number would be coming, this is positive r, and so your negative r would be going this way. So as you go around of r is equal to sine theta. So what do you think that graph is going to look like? So we know that if we were to draw this in regular Cartesian coordinates, which is not what we would normally do because we would have x and y coordinates and then r and theta to be what those r and theta are, your graph would look like this, right? But now let's transfer that onto the x and y. So when theta is equal to 0, or when theta, yeah, is your independent, r is your dependent. When theta is equal to 0, sine of 0 is what? 0. So it looks like I would be here. Maybe I need this arrow a different color. Did it change? It didn't change colors. Oh, there it goes. I can't see. Now, as you move, it's kind of moving. What? No, it's not supposed to get shorter. Well, according to this, as you move, you're going to go from 0 to a length of 1, right? When does this happen? Pi over 2. Well, this I'm not at pi over 2 yet. So before pi over 2, like I'm at root 2 over 2, right? So I would go from 0 to root 2 over 2. And then as I keep moving this, it would grow to 1. So pi over 4, root 2 over 2, pi over 2, I'm at 1. So then I would have something that might look like this, right? Now, if I keep going, I see by the time I get to pi, I'm back at 0. So I keep following my ray going down here, it's going to shrink back down at 0. So it looks like it might be a circle. I don't know. So I'm down here at pi. Now, if I keep going around, I'm going to go negative. So as I go around here, like this is pi, 5 pi over 4 maybe, I would be looking at a negative value from there. I would be looking at somewhere over here, right? So it looks like I have the potential to trace out the exact same circle, except I'm tracing it out. If I'm like looking at myself going forward as my R, if I'm going negative, then it's behind me. So that's like me looking this way, but tracing out what's behind me, right? And then it's going to go down to -1. So by the time I'm down here, I'm at -1, and then I get back up this way, and then I'm down to 0 again. Okay. That's interesting. Let's graph it. So at pi over 2, I'm half a circle. At pi, I've completed the whole circle. And then at 3 pi over 2, It looks like a complete circle again, but now we have to remember that it's probably redrawing itself backwards. Okay? So that's another important observation. So this is a sine, and this sine completes the circle from 0, whoops, that's theta, from 0 to pi is one complete circle. Okay, is that interesting? That is pretty interesting. Yeah. Yes. No, don't rethink everything yet. Okay. Thanks, Jake. Anything else? All right. I'd be interested in having you guys do activities, but I think we're kind of in a rush here because I want to get through a couple more graphs. Without calculators, computers, just for a minute, think about what do you think the cosine is going to look like? Starts at 1, right? When theta is equal to 0, it starts at 1. So describe this to me. By the way, we didn't label this. This is 1, and the middle is 1/2. All right. Cosine? And at the origin, and then come back. So that's your cosine function. All right. So that's interesting. But now let's take a look at more interesting graphs. Let's take a look at r equals 1 plus sine theta. Now for that, it'd probably be good to take a look at how this is. The sine theta looks like this, right? What's 1 plus sine theta? Shift it to the right? To the right? I think it's shifted up. There you go. Let's imagine how this is going to look like. So at 1, right? Or when theta is equal to 0, we start at 1. This is 1, max height at 2, and then 0. So it starts at 1. And then what happens? It gets bigger, right? Gets bigger. And then by the time it gets to pi over 2, it's 2 units away. And then by the time it gets to pi, it's at 1 again. Now, what do you think is going to happen? It's going to go down to 0, and then it's going to come back up at 1. What do you think is going to happen? Imagine that ray going around, goes to 0, and then bounces back up. What are you picturing? Anything? Kaleo's going. Goes down to 0, bounces back up to 1. Happy Valentine's Day. It's called a cardioid. Okay. Let's try another one. So 1 plus 2 sine theta, amplitude 2, shifted up 1. So amplitude 2, shifted up 1. The sine. So let's see. Starts off at 1. Then it climbs up. By the time you get to 2, it climbs up to 1, 2, 3. And then by the time we get to pi, it goes back to 1. And then it starts going this way. And then it goes to 0 a little bit sooner. So this is going to hook up to 0 before we get this. It's going to hook up to 0 at some weird angle over here, whatever this angle is. And then it's going to go negative. So now, tell me, what do you think will happen? All right. It goes negative. Anybody speak French? This is called a limaçon. Whatever. Yeah? Do you speak French?
I think it is.
This is that C with a little curve underneath.
Yeah.
C, limaçon. Sure. All right, so here are the last 2 graphs that we did. R equals 1 plus sine theta. Cardioid, R equals 1 plus 2 sine theta. And then if you change this into a cosine, you can try to imagine what would happen. But if I show you, it just means it's going to go sideways. So that's related to the circles, just regular sine theta and cosine theta. One's up along the y, one's up along the x. The cardioids and limaçons happen the same way along the y or along the x, depending if it's sine or cosine. Okay, so that's a bunch of polar coordinate graphs for you. I encourage you to go to Desmos and try out a bunch of sine and cosine graphs, or even some other graphs. And then when we come back tomorrow, we'll do some calculus on them. Derivatives, tangent lines, and maybe integrals. Okay, see you guys next time.